Welcome to my talk with the title Climate and Relief-Induced Controls on the Temporal Variability of Denudation Rates in a Granitic Upland. The presented work is, of course, a collaboration of several institutes, and I also thank on this point all my partners. My name is Gerald Raab. I'm currently a postdoc at the University of Zurich and also lead investigator of the presented research. My talk today will be structured into two parts. I will start out with an introduction into the research field and our main focus of our work. And in the second part, I will then spend my time on the invited talk. I've been asked to give a talk about the presented topic, which is found in Earth surface processes and landforms. So let's get to it. Let's go to the introduction. The talk is about surface denudation, erosion, and as you can see here in the world map for soil erosion done by the FAO, we see that it's quite an issue, especially in mountainous areas. Um, I'm from Europe, so Europe is of course one of the key interesting points for me. And as you can see on this map here from the EU, that the potential soil erosion risk in Europe is quite rising, especially again in mountainous areas. However, we have one issue in all this erosion investigation and surface denudation investigations is that we have a lack of long-term data. And with long-term, I mean over the last hundreds, thousands of years. And this is particularly the case when we talk about soil erosion and so. And for you to better understand why there is so little information about soil erosion variations, I briefly guide you through the conceptual idea of soil evolution. So this is from Johnson and Watson-Stegner. And we start here with soil over time. We start off with progressive pedogenesis, where soil is formed, and soil forms very easily when soil forms very easily when production is larger than surface denudation, of course. Let's say denudation and erosion is more or less the same for our sake. Of course, weathering and other factors should be included, but it's more or less equal here. Once we reach at the point, the tipping point, where surface denudation overtakes production rates, of course, soil is not formed anymore. We go towards regressive pedogenesis, and this is, of course, then through soil shallowing, especially through physical erosion. And when we looked at it today, we only see this present information, and this upper part, this past surface evolution, is actually lost. Therefore, capturing these past variations of surface denudation with particular soil erosion remains very challenging on site. And currently, what we do is we use indirect archives in order to estimate the rates within our areas of interest. For example, these are usual archives that we have, like lake sediment records, speleotene growth rates, river sediment bills, marine sedimentation records, and so on. And all these catchment-wide approaches are usually used to describe what is going on in the backland, so in the denotational zone itself. However, these archives, these catchment-wide approaches, can have been interfered with over time as well. So they could have changed, and they do not provide always a full coverage for the denotational zone, and also they only provide average rates and rarely the deviations. Within the denotational zone, however, we only have very few methods. For example, so weighing or isotope methods, which I can show you here in this picture, where you simply put the stick in the ground and you just measure how much soil has been lost over time. And the issue with these methods is that weighing and this, isotope methods cover only a very limited time span, so the last 100 years or so. And therefore, we have actually a lack of methods. And this is where my research focuses on. So to try to identify new methods, to develop new methods, to target especially this research gap of methods to quantify surface denudation rates within the denotational zone itself. And over the last years, we came up with an idea about testing a new approach by using TORs. So tors are these large residual rocks that are still attached to the bedrock, which can be there in a variety of shapes. Here's, for example, another picture how they can look like. And we thought that these tors are potentially an archive, and if we can use their exhumation patterns, if we can decipher it, we might be able to determine surface denudation rates. And we based this idea on deformation theory. So here from Migon, so you start off with this fractured rock mass, and then you have this weathering mantle going to be formed. And once this weathering mantle is eroded away, then these tors, so these large residual rocks that are still attached to the bedrock, remain. And we thought, yeah, maybe they inherited some information. So the conceptual idea was very simple and very straightforward. So if you imagine, for example, a popsicle and the tor, over time, the ice gets eaten away and also gets the surface stripped away. And as the ice color tells us something about the past, we thought about isotopes in the rock surface. And in our case, we mainly focus on cosmogenic nuclides. So for those of you who are not familiar with cosmogenic nuclides, I'll give you a brief introduction. So Earth is constantly bombarded with cosmic rays, as you can see here in the background, where also spallation happens. So these are all these reactions. And these spallation reactions can occur not just in the atmosphere, they also can occur within the rock surface, in particular then within the mineral assemblage. So for example, if you look here at this assemblage, we take out quartz. And because quartz is also built out of different elements, as we know, so lithium and oxygen, they can also spallate into different other isotopes. And because it happens within the rock and within the mineral itself, it's called in situ. And because they're trapped within this mineral lattice, they do not get out and start to accumulate over time. And we extract actually then certain isotopes and measure the content, and this allows us to determine the surface ages of this rock surface. And for our research, which I present today, I will focus mainly on temporalium. And this brings me to our main hypothesis. So again, we have our tors that get exhumed over time, and then we add just this temporalium accumulation. And again, we think that the content should increase from bottom to top, and therefore also the surface ages should be increased from bottom to top. And by determining the exhumation speed of the tor, we should be able to actually get surface denudation rates. So this was our main hypothesis. And now I come to our research results in our wonderful study area. As you can see on this picture, we are in an upland plateau area, gentle rolling paleo surface, which is found in southern Italy at the wonderful Sila Massif. It's tectonically stable. It has a consistent ecology. There are no large material influxes. There have been no glaciation. So a perfect area to study our new approach. And we started our sampling in the center of this massif. So here a picture of the here map of the sampling site. And as said, we investigated a couple of tors. So 5 tors were investigated, and the sampling strategy was very straightforward. We sampled from top to bottom and have taken our rock samples there. And again, we expected higher content, old ages on top, and lower content and younger ages on the bottom. And in addition to these 5 tors, we also investigated a couple of boulders and a couple of scarps to see how these compare to tors. So we do not single tors out. We also wanted to compare how it behaves in contrast to other landscape features within the same landscape. So again, we went into field. We have taken our rock samples. We did some target chemistry, extracted temporalium, and then we got our temporalium content. And these are the results. So you see here a graph on the left side, you see heights of ground. On the X scale, you see the temporalium content. The first thing that comes to notice is that we have an increase of content from bottom to top. And this means that our main hypothesis appears to be at least partially valid. Also, for example, if you look here at tor number 5, you see a really nice trend here indeed as well. Also here, tor number 1, you have really great trends found. For example, if you go here to number 2, we can look at surface ages. These are the sampling spots. We've taken our rock samples. Of course, we included this big chipped area because some part has fallen off here. And these are then our surface ages. So surface ages are presented in kilo years. So this is like 106,000 years, 98,000 years, 31,000 years, and so on. And again, we have this increase of surface ages in average. And we can plot this, of course, in a classical XY diagram. Again, we have age on the X and heights above ground on the Y scale. And for the age calculations, we also applied, of course, rock erosion rates. This is what the RE stands for, so rock erosion rates, as this also impacts the actual surface age which we calculate. And we use then these surface ages and some Monte Carlo simulations to determine their potential exhumation path. So we did different regressional fits. We used functions of Lichter and also logistic functions to determine the different path. And when we use then the first derivative of these functions, we resulted then in our wonderful surface denudation models. So now we have a great model that goes from Pleistocene, goes back to Pleistocene, and covers now a large time span and this continuously, so not just averages, but also it shows some variation. This is just now for one core. Yet, how do our boulders compare and our scarps? So a quick look to our boulders. So on the bottom, you see again temporalium content to heights above ground, yet there's not really a clear trend. It's spread all over. And this is also the case with the surface ages. So you have 22,000 years and 24,000 years on top and bottom, so really the same. You have ages spread all over with older ages on the bottom and younger ages on the top, and it's very spread. And yeah, that doesn't really allow you to give any trend or have any clue what happened precisely with these boulders. If you look in our scarps, we see partially a trend here. For example, for scarp 2, you see here partially a trend. However, when we look at the surface ages in total, they're all very, very young. So they don't allow us to go very far back in time. For example, here, image C, you see this is like 50 meters or between 40 and 50 meters long ridge, and we still have more or less the same surface age for the whole ridge. And this just shows, okay, they have been exhumed very, very quickly. In summary, just for these boulders and scarps, for these boulders, we thought, okay, they probably have toppled or have just grown out and yeah, toppled over. And yeah, well, they don't really give us a good estimate as a new surface denudation archive. The same goes for scarps, as they only cover very limited time amount and have been exhumed probably simultaneously, very, very quickly in more or less at the same time all over the place. And in contrast to our tors, which reach really back to 100,000 years and have more continuous exhumation path. So this brings me back now to our tor. So this was the model we talked before about this tor, but this was just one tor. And as said before, it reached back continuously up to the Pleistocene. Yet when we looked at all the other tors as well, not just at tor number 2, we found out some very interesting extras. And this is also stated already in the title that we have some relief-induced surface denudation control. So when we look here at an elevation profile along our sampling site, and we looked at where our tors are positioned, we looked at the different models of the individual tors, and we found out they actually correlate very well when we dissect the elevation profile into different sections. So the first section would be the slopes. So the slopes are relatively young, as expected, as we also have seen from the scarps, they're relatively young. And they have also the highest peaks of all of our other tors. In contrast to the ridge top here that has been exhumed more continuously last 100,000 years and has more continuously rise of surface denudation trends. In contrast, then, if you look at the more planar surfaces here, so it's not that steep as at the slopes, they have been assumed at a similar time than the slopes, yet with a much lower peak. And therefore, we see this relief-induced or this topographic control on surface denudation rates. And it's very unique that we see with this approach, first of all, the variations, not just the averages, and we also see the topographic effect on surface denudation rates. Of course, we compared it then to catchment-wide derived rates, and again, as said, first of all, they fit to the average rates here from Olivetti et al. But we can show with this approach the variations, not just the average. When we think about our research gap, we can say that this Tor exhumation approach, so this T, this is how we call it T or T, Tor exhumation approach, can fill parts of this research gap. But of course, there's still something to investigate. And once we have figured out that this topographic effect occurs, we immediately ask ourselves, how do modern rates compare to our long-term derived rates? And here's like a combined model for our C2-temporilium-based model. We have a surface denudation model here. We have surface lowering rates on the right Y scale, and again in tons per square kilometer here, also soil erosion rates on the Y scale on the left side. And these are pure derived rates. They have, of course, a large variation. This is just an average. However, when we look here, we see, of course, we have this trend going down overall, and we have this peak here around between 10,000 years. Then we have this research gap, or still a informational gap, as you have no data for this time span. And then we have this large rates in modern times for the last 60 years, 70 years or so. This is what Pew covers mostly. So of course we ask ourselves, what timeline? So what happened at which time? Why do they vary in the first place that much? And this brings me back to our surface denudation model with the individual positioned tors. And we added an information from different other publications to get one consistent model for this one upland. The first thing we got is other surface and soil ages to harden the data that we have to really identify and say, okay, well, the estimations that we made with this model and the surface ages of our tors fit with other surface ages as well. And we've done an investigation a couple of years earlier where we looked at volcanic material that has been deposited at sea level. And there we found that all those volcanic deposits are around this time, which fit to our ridgetop tor. And the average soil ages is around 45,000 years. And we also estimated with some weathering indexes oldest and youngest surface ages. And the youngest surface ages fit very well here with the rise of this slope and basin tor found surface denudation rates, which means that not really much soil has been stored or produced, formed after this time. And then, of course, we added some climate information. We looked, okay, what were the climate conditions, at least the wake conditions for this area, as good as we could. We had here warm and humid and cool and dry, warm and dry, cool, dry, and again, warm and humid. It's all by Allen et al. And in addition, we also looked at vegetation. So how did vegetation change? We had the dense forest, and we went over to steppes, and now we have also a forest which has been changed actually to mixed forest nowadays by humans. And we thought, okay, there are all those volcanic deposits still there, so progressive pedogenesis probably must have happened here. However, we only have known surface denudation rates and not the production rates in order to see if we have soil formation. And so we looked at soil masses and surface ages of different soils, volcanic soils, Mediterranean soils, andesites, alpine sites, and so on, and used some very simple correlations to determine surface age to soil formation and production rates for different soil types. For example, if we say our soils are now around 10,000 years, maybe 15,000 years, and the production rate is around 100. And we played around with these numbers to determine when there was a progressive, probably a progressive phylogenesis, a balanced and regressive phase again. So for this earlier soil times, so these earlier stages here until around 66,000 years or so, there was probably progressive phylogenesis with soil deepening, so really good soil formation. Later on, we joined the balanced phylogenesis, where soil production equals surface denudation, and this was then followed at this tipping point around 15,000 years with a regressive phylogenesis, where, of course, soil shallowing happened through physical erosion increase. I want to point out here that we had our model saying that the surface denudation decreased, probably because surface vegetation also become more dense and therefore held back some of the erosion at the slopes. However, modern erosion rates from the plutonium rates are much higher, and we think that this is mostly through human induced influences. And I also want to point out that under similar conditions, so we have both warm, humid, and both with forest, very opposite soil forming conditions. And therefore, for these earlier stages where the soil was relatively young and the surface was relatively young, we had, of course, higher production rates, and therefore soil formation was much easily possible. In contrast to nowadays soils, which of course had to change from this cool dry to this more warm humid conditions with much lower vegetation, as it was a step B covered area, and the soil had much less capacity in order to produce soil and therefore form soil. And this brings me to my conclusions. So again, for our research gap, we have seen that the tor exhumation approach could fill part of it. We could see that tors are a good tool to determine past surface denudation rates continuously over geological timescales, and of course in situ within the denudational zone. I've shown you that through the climate change, so Pleistocene Holocene transition, for this area we have this increase of surface denudation, and the denser vegetation probably counteracted until, of course, human interaction came into place. And most importantly, I clearly could show you that topography determines the extent of surface denudation in this upland. So these are the three key factors that we found for this area: climate, vegetation, and topography. And on this point, I also thank you for your attention. I hope you enjoyed the talk, and if you have any further questions, of course you can ask me now, or you can go to my website. It's www.geraldraab.com, and there you can also send me a message and get in contact with me if you have any interest or any further questions regarding my research. Thank you again.